As we begin a very in-depth look at measurements, I want to glance at our previous video where we had said that quantities are measurable properties. And when we're trying to measure things, it's absolutely critical we standardize the way in which the measurements are made, the techniques, and the units that we use. And the reason for that is there are tons of units possible for each quantity, and we don't want to have to convert among them. And also, the historical origin, the definition of these units has changed over time, so we want to take a look at things that are meaningful on a universal scale. And to do so, we've got this SI measurement system, the Système International, and it's based on 7 base units. So they're fundamental units based on universal constants, all right? Fundamental units based on universal constants. And this is actually a huge deal right now because it is the year 2020 and our pre-existing definition of those SI units has changed. As a quick reminder, because it's super important, we had said that there are quantities and there are units, and quantities are these measurable properties like time and length, etc., whereas a unit is a specific way to describe those quantities. And understanding this relationship is going to be key for dimensional analysis at a later point in time. So I want to keep the idea of a quantity and a unit fresh in your mind. And now let's just glance at these pictures that I printed out from Wikipedia of the new SI definitions and the old SI definitions, and they revolve around these numbers right here. Okay, if you look, I had said it's based on universal constants, and most people know of at least one universal constant, which is the speed of light in a vacuum, 2.9979 times 10 to the 8th meters per second. All right, so that is a universal constant. And this 2019 redefinition of the system then uses other things like Avogadro's number, which is familiar to some of you perhaps, Boltzmann's constant, the elementary charge, that's the charge on an electron, Planck's constant, and the frequency of cesium transitions. So, and then this other constant, K sub d. If you look, I tried to color code these right here. They are the same 7 base units. I looked at a few different websites to get these drawings. I like these because it visually relates how things go to each other, although they look like a horrible mess at a first glance. But looking at how the second was defined, that hasn't changed, all right? So the definition of a second has not changed, and you can spend a long time talking about how these definitions work, but this thing that looks like a V is frequency, so how often something happens, and this how often is related to a specific isotope of cesium. Now, if you look at the kilogram, it used to be based on, pre-2019, a metal cylinder in a jar in France, which is not such a good universal constant, right? Because A, there's only one of those, and B, it was changing over time. So, big red flag on that one. We don't want the old definition, which was based on a metal cylinder in a jar in France, which is not universal at all, but now it is based on Planck's constant, all right? So a universal constant, 6.626 times 10 to the minus 34th joules times seconds. So gone, and that was in previous years. That's always the one that I really made fun of because it's horrible. And now we have this based on a universal constant. If we look at the mole, which is a concept a lot of people aren't familiar with, early in chemistry, although it's fundamental for the rest of the year, it used to be based on carbon-12. In fact, it was the number of particles in 12 grams of the isotope carbon-12. And so that's not super convenient to use because you can't count those. 6.022 times 10 to the 23rd is a huge number. But if we just declare Avogadro's number, that's Avogadro, who is an Italian scientist, and Avogadro's number as 6.022 times 10 to the 23rd. And in fact, if you glance at our little list here, we had for Avogadro's number 6.022140076. And they declared that is an exact number. And that makes things a little easier. Now, the candela, and we'll write these out, I guess, in a little bit, but the candela is a measure of luminous intensity. And if you really want to give a basic definition, that's how bright things are. And historically, you could say, oh, a candela is based on a candle. And it is, all right? But you can't universally standardize how much light is given off by a candle. So they do this stuff with black body radiation, etc., etc. And that constant, that was a constant previously, and it's going to remain present in the revised SI measurements. If you look at Kelvin, which is an absolute scale for temperature, it used to be based on the temperature of the triple point of water, all right? So it turns out that there's a temperature at which water exists simultaneously as a solid, a liquid, and a gas in equilibrium. Now, that's not super convenient to work with, and there is some variation depending on things. And so they decided to change that definition to Boltzmann's constant. And we'll talk a little bit about that Kelvin temperature scale and why it's so slick. It starts at 0. And absolute zero is a term you may have heard before, where there is total absence of heat. So now it's based on a constant. So this has changed rather than basing it on water. Now, over here we have our two different definitions for the ampere. And the ampere is a measure of electric current. And if you've ever had in your house, like, you believe it or not, you've got current ratings on things all around you all the time. But for example, if you've ever blown a breaker in your house, like you plug in a couple hair dryers in the same outlet in your bathroom, then someone goes to the breaker box in your house somewhere, and there are little switches that you flip back and forth. And those switches have numbers and letters on them. They might say something like 15A, all right? And that means 15 amperes, and it's a current rating. And current is really how many electrons are passing through that wire in a certain amount of time. So if you exceed, for that breaker, 15 amps, so that many electrons passing that point in a certain amount of time, then the switch flips and it won't let those electrons go past anymore. Because if they keep going past, you risk some type of fire or something bad happening, right? So it makes sense that we would now define the ampere on the charge on an electron, which is 1.60, with all those other numbers, 10 to the minus 19th, and that is in coulombs, all right? So the ampere related to the charge on an electron. So that has changed. We no longer use, this definition was based on the interaction of some charge field between two parallel wires, blah, blah, blah. So not convenient at all, whereas if we just declare the charge on an electron as one that we're going to use, then that works out very, very well. That leaves our unit for length, which is the meter. And if you look back historically, I think this is the easiest one for us to ponder. I always ask my students, I'm like, what is a historical definition for something, a measurement of length? And people will often say, oh, the foot, right? And then if we make up a story, like the original foot was probably based on the length of a foot of some person, which isn't a good universal constant because different people have different feet. And if you don't have that foot around, then you don't have that exact measurement. So, you know, eventually we will get to the idea of like a yard or a meter, which I think was based on the distance from the tip of a man's finger to his nose or something, with his arm outstretched. And then eventually it was like 1/10,000th the distance from the North Pole to Paris or something. And that's not super standardized for many reasons, one of which is that number's changing drastically. So if we're going to base it on some universal standard, then it's convenient for us to use something like the speed of light in a vacuum. And so you'll notice that has stayed the same over time. I just noticed that I messed up my labeling scheme here. This stayed the same, this stayed the same, this changed. So if this changed, I need to put my red circle around this. If this changed, this needed a red circle. And then this one did stay the same, so I will need to put my star on that. And that's not some universal labeling system, I just made that up for this. But as you look at it, using our constants, now we've changed 1, 2, 3, 4 of these, rather than measuring things in some oddball way. They're just based on some specific constants that were established.